Howdy and greetings, friends. Welcome back to the sequence of my YouTube videos that I hope will be helpful to you as you are beginning your career in um, electronics technology. We are having a really exciting project today. We're going to talk about voltage dividers, potentiometers, shorts, ground analysis, and how this all is analyzed on your breadboards. So without further ado, let's go ahead and check out what we have. All right. What is a voltage divider? A voltage divider is a very useful learning tool to better understand how voltage and resistance and current behaves in your series circuits. I have a schematic on the far left-hand side of the screen that goes to show a series circuit. We are implementing a new schematic symbol here. This is called ground. I'll define what ground is in a moment, but don't get this confused with earth ground. This has nothing to do with the little ground lug you have on the wall. This is a electronic technology symbol, and you'll see how it's used in a moment. You're familiar with the resistor symbols. I have three of them, R1, R2, and R3, one voltage source. Voltage source is a DC voltage source specified at 5 volts. R1 is given as 300 ohms. R2 is 100 ohms. R3, oops, come back here. R3 is 220 ohms. Now, I've expanded the drawing into this analysis where I've attached a voltmeter. Voltmeter number 1 is physically attached across R1. Here's R1 in the original circuit. I'm attaching a voltmeter that will be attached to the top of R1 and the other lead of the voltmeter to the bottom of R1. Then we're going to analyze separately using voltmeter number 2. It's designated as VM2. I have a second voltmeter and it is across the second resistor. I have a third voltmeter which is across the third resistor. And I have a couple of ammeters in here. Ammeter, as you recall, measures current. And current is going to be measured here at the top of the circuit, going to be measured here between R2 and R3. It's going to be measured here between R3 back to the negative plate of the voltage source. There is one more voltage voltmeter, VM4. VM4 is connected directly across the power supply and will give us a reading as to whether or not this is a true 5 volts or not. Now, notice the yellow arrows. The yellow arrows indicate the direction of electron flow. Electrons, as you recall, leave the negative plate. Negative plate is the shorter of the two plates that are shown, the two lengths of plates. So I have long, short, and the combination of those four designates a DC power supply. And the short plate is where the source of electrons are. So they do leave the negative plate, flow down, hits this node, and makes a turn to the right. How come no current goes to the left? Is because all voltmeters do not allow any significant current going into them. They have what we call an infinite resistance in their connecting terminals. So since no current is allowed to go towards the voltmeter, all the current is forced to flow in this direction, hits this node. The node is a connecting point of a number of electronic components. So these dots are called nodes, and it's got to go up. Remember, no current's going to flow out through this path to the voltmeter. The voltmeter is, with its infinite resistance, does not allow any significant current that will be measured by us. So the current's forced to go up through ammeter number 1, up past this node, past this voltmeter. No current goes into the voltmeter. It just continues up through R2, the 100 ohm R2, continues up through this jumper wire and goes up to R1. Again, no current flows out to voltmeter number 1. The current flows through R1 and then makes a turn to the left, flows through ammeter number 3, and then at the top of the circuit hits this node. And again, no current goes through the node to the left because the voltmeter does not accept current. And so the current is forced to flow downwards back to the source. So as you can see, we have a continuous path for electricity to flow. We have what's known as continuity. which allows electricity to flow through R1, R2, R3, and through these ammeters. And while electrons are flowing through, we will be able to see how voltage can be measured at various places in the schematic. I have a table of measurements, which I'll define in a later slide, but this goes to show all of the measurable parameters that this particular schematic can reveal. Very interesting. Next. All right, just as a reminder, you'll find this instructor to be probably one of the most redundant that you'll ever come across, and that is I will be continually reminding you of things that you should always have in your journal. As long as you journal things, it's written down. You can always flip to the page and be reminded without me reminding you. However, since some of you have not started your journals or your journals are not up to date, please write all these information down if you have not already. Circuit requirements. What's needed for a circuit? An electronic circuit, complete electronic circuit, must have the following. There's 4 bullet points. Number 1, a complete electronic circuit must have a voltage source. The voltage source is what provides the pressure to move electricity. Number 2, your circuit's got to have connecting wires. If you don't have connecting wires, the electricity's got no place to flow. So the connecting wires provide what we call the pathways for electricity to flow in a circuit. Thirdly, what you're going to need is something called a load. Now, we defined a load in a previous topic video as any device that has electricity flowing through it, such as a resistor. Now, a wire generally is not considered a load unless it's a very, very long load, long wire, such as what you have from your transmission towers out in the valley coming over to the metropolitan area. Those miles and miles of wire can represent some load, but the loads we're talking about on our breadboards will probably be LEDs and resistors and things of that sort for now. Then number 4, most importantly, you have to have continuity. Continuity is defined as an uninterrupted path for current to actually flow. So let's analyze the circuit on the left. Let's analyze the circuit on the right. The circuit on the left has the first 3 circuit requirements. It has a voltage source, it has connecting wires, it has a load, but guess what? It doesn't have item number 4. It has no continuity. How do we know that? This switch is popped open, so it is called an open circuit. This thing will not light up. Circuit on the right has all 4 circuit requirements. It has a voltage source, connecting wires, a load, and because the switch is down, it has continuity, and therefore this closed circuit, the nickname for this is a closed circuit, is defined as being on, and if all the other parameters are in good standing, the light bulb will light up. The DC light bulb will light up. This DC light bulb will not light up because we have an open circuit. All right. Now, some characteristics of series circuits we hadn't talked about because we'd only had 1 resistor in our circuits previously. This go around, we're going to have 3. So let's see what are the characteristics. Number 1 on the left, series circuits divide voltage. What do we mean by that? What we mean by that is this 9-volt source, which could be a 9-volt battery, will have part of its voltage measurable across R1, part of it will be measurable across R2, part of it will be measurable across R3. So that 9 volts is going to have a chunk measurable across each of these resistors. So that's how series circuits will divide the voltage. Series circuits are also known by a nickname. They're called a string. And if you look at the illustration that's shown here, this shows a single wire loop with 3. These could be Christmas lights of sorts, and they are a singular current path that shows electricity flowing, and so the nickname is called a string, much like a string of pearls, a string of beads. They're all one string, and they're one right after another, such as these little DC lamps are. Number 3, current is the same throughout a series circuit. Take a look at the formula here. I total is equal to the current through R1 is equal to IR2, current through R2, And through as many resistors as we have in that circuit, if it's a series circuit, all the way out to number n, whatever n is, it's a variable. So if we have 15 resistors, then it's all the way up to R15. So what we have here is current is the same throughout a series circuit. Hold these thoughts, jot this information into your journals now. You won't regret it because we will be referring back to these concepts very shortly. The largest ohmic resistance will drop the highest voltage. What that means is if we look at these three resistors and we measure voltage across each one of these, the 300 ohm resistor will have the largest portion of the 9 volts. It won't get all of it, but it'll get most of it. Then the smallest ohmic resistance will drop the smallest voltage. Now, the drop is a very common term that we use in electronics, and it just simply means a voltage, a certain amount of voltage from the source is measurable across a resistor. Certain amount of voltage is dropped across that resistor, across each of these resistors. So it turns out that the smallest ohmic resistance will drop the smallest voltage. Which one of these is smallest? 50 ohms. So of the three resistors, the portion of 9 volts that is measurable across the 50 ohm will be the smallest. And it says here in the next bullet point, the drops are proportionally distributed across the series resistors. The proportional distribution is shown in what's known over here, the voltage divider formula. The proportion of voltage across any resistor, Rx, X being the variable, could be R1, R2, R3, is equal to that resistor's ohms divided by the total ohms times the voltage source. I'll go over these in detail with math, and you'll be practicing on your calculator very shortly. So this is not a hard concept. Jot it down in your journal. The circuit will be what? The circuit will be off if there is a break in the circuit, like a switch being open, yeah? Now, these are very common formulas. You should jot these down in your journal as well. Total voltage is equal to the voltage across R1 plus the voltage across R2 plus ... all the way to the last resistor, whatever that might be, 15, 18, 3, 4, whatever. So voltage total is the sum of each of the voltage drops across each of the resistors. Current total, however, is quite unique. Current is the same through each of the resistors all the way out through the last resistor. And you'll see that when we measure it very shortly. R total is the sum of the individual resistors in the circuit all the way out to ... Rn. So how many resistors do I have in this schematic? 3. Add them up. What's 100 plus 300? That's 400. What's 400 plus 50? That's 450. So the R total for the circuit that's shown here would be 450 ohms. And that's calculated using this formula. I'll give you the formula for power now. We're not going to use it for quite some time, but put this in your journal. And then the voltage divider formula is abbreviated as VDF. VDF standing for voltage divider formula. And you can see there's a fraction, a portion, a piece of, like a pizza pie. How big is the voltage across this slice of a pizza is determined by the size of that slice divided by the whole pizza times the total voltage. That's kind of a not so elegant analogy, but the voltage across any resistor is defined as a portion of the whole. And here's the whole. And what portion? It could be a half, it could be a third. It all depends on this fraction. And how do I determine the fraction? Well, if I wanted the voltage across R1, I can calculate that now by taking 100 divided by the sum. So 100 divided by 450, and that will calculate the amount of times 9 volts. That will calculate the amount of voltage across R1. Okay, let's show you with another example in detail. Here we go. So given the circuit that I've shown you at the very beginning, and the one that we're going to be building shortly, it says, and these are snips from the data analysis from my simulation software of voltages and currents of interest. So the first characteristic of Series circuits. Series circuits are said to divide the voltage. Well, the source is 5 volts. How much will voltmeter number 1 measure the voltage drop across R1? It turns out, according to the simulator, 2.54 volts. If everything is ideally perfect, if this is a perfect 5.00 volts, and this is a perfect 330 ohms, and this is a perfect 100, this is a perfect 220 ohms, for a total of 650 ohms. If in an ideal world, we would have an ideal voltage drop about 2.54 volts. We'll see how close we come with our circuits in a moment. The voltage across number 2 shows 769.23 millivolts. We're going to be introduced to engineering notation on your calculators in a moment. So it's less than a volt. Interesting. And then the voltage across the third resistor, measured by VM3, voltmeter number 3, is predicted to be 1 point, well, actually in the simulator, it's not predicted in the simulator, it's actually stated to be analyzed to become 1.69 volts. So that's how 5 volts has been divided across each of the 3 resistors. Next, series circuits are voltage dividers. They're known as a string, all right? Basically is another way of saying the first bullet point. Third bullet point, current is the same throughout a series circuit. Now check this out. Look at this carefully. I have ammeter number 1. Ammeter number 1 is between R2 and 3. Ammeter number 2 is between the negative plate of the voltage source to ground to, come back here. Between the negative plate of the source, ammeter number 2 to connect to the bottom of the circuit. Ammeter number 3 is at the top of the circuit between R1 and the electricity flowing back to the positive plate. At 3 different ammeters in 3 different places, and guess what? The software says it should measure 7.69 milliamps. And again, we get into this engineering prefix, which we will practice very, very shortly. But the most important thing is they are the same value. We'll prove it in a moment. And check this out. Next bullet point, largest ohmic resistance will drop the highest voltage. Is that the case? 330 ohms is the largest resistor of the 3, R1. And guess what? It has the largest amount of voltage divided across it. Take a look at here. Smallest resistance will drop the smallest voltage. Well, R2 is the smallest one. It's only 100 ohms. And guess what? It has the smallest voltage to drop. So these rules, these principles of series circuits are validated by this software, and also will be validated shortly with your circuit boards. Come back here, sorry. Okay, then finally, voltage drops are proportionally distributed across series resistors. And we'll show you that proportion as we calculate it in a moment. And finally, over here, circuit will be off if there's a break anywhere in the circuit. There's a wire that's not connected properly, no current flow, no continuity, circuit is off. Okay, now let's talk about VDF, voltage divider formula. Same circuit on the left. Now, here's the formula, repeated. You've seen it before. You have it in your journal, I hope. We need a total for R total. R total is a key value that we need in this formula. And you've seen in your notes, as well as on a previous slide, how do I find R total in a series circuit? It is the sum of R1 plus R2 plus R3. So if I add these together, I get 650 ohms. Next, how do I apply voltage divider formula to find the voltage across R1? It is given as a fraction. R1, voltage across R1 is, in parentheses, R1 divided by R total, close parentheses, times V total. V total is the same as V source. So 350 divided by 650 equals, then times 5, gives you 2.54 volts. The voltage across R2 again, the fraction we set up because we want the voltage across R2. What do I put in the numerator of the fraction? I use the ohmic value of R2, which is 100 ohms in this case, divide by 650 total ohms, close parentheses, times the 5 volts, and I get 769.23 millivolts. Okay, and then R3, using same method, the voltage across R3 is the ohms of R3 divided by the total ohms, 220 ohms divided by 650 ohms times the 5 volts is equal to 1.69 volts. These should be your calculated results, and we're going to run through these calculations in a moment, prove this to ourselves, and see if all of this jives on our calculators. And then just for giggles and laughs, you should know from Ohm's law that your I total is equal to your V total divided by R total. That's equal to 5 volts divided by 650 ohms. We will have a current that is 7.69 milliamps. So hold that thought about the current and calculating I total. We'll go to the next slide. All right. Before we go to switching to the camera setup for engineering prefixes, just wanted to review these things with you. First of all, the recommended calculator is the CTI-free FX991MS. It is basically a Casio that has been updated. I have a Casio FX115MS. It has been updated to this one, and it has a few more functions than the predecessor. But they both are capable of the same thing. And actually, today's calculator is less expensive than when I purchased this one many years ago. What do we have going on here? What I want you to pay attention to is these calculators are the ones that are recommended. Why? Because they make your calculation at this stage of your education much easier to follow. You can do this without these calculators as long as you have an times 10 key, EXP key, and an engineering key. As long as you have these two keys on any scientific calculator, you can get by, but you just won't be able to see the engineering prefixes. So on these calculators, if I were to take 8 volts and divide by 458 kilos 1,000, if you remember, is shown by the letter K. I can enter that K because I have the letter K right here as a second function. And when I enter it this way and hit equals, my calculator here shows the engineering prefix, which is micro. So this would be microamps in this case. Now, before this calculator is set up properly, this calculator, right out of the box from our friends at Amazon, will initially give you this visualization. 8 divided by 450 kilo gives you scientific notation. Scientific notation is useless to you and I for our studies. Scientific notation is defined as 1 digit, 1 decimal point, followed by a number of digits to some power of 10. And if it ain't a power of 10 that happens to be some kind of multiple of 3, it's useless to us. So we need this converted into some power of 3. So if your calculator, some multiple power of 3. So if your calculator, scientific calculator, it could be a Sharp, it could be a HP, it could be something else, doesn't matter what, doesn't have the engineering prefix buttons, you can still change scientific notation to engineering notation just by hitting this ENG key. You have that on, hopefully, on your calculators if you choose not to add this one to your repertoire. And it's at its price, I think it's definitely worthwhile for you to have. Let me just ask you this. How many pairs of shoes do you have? Come on, think about it. How many pairs of shoes? You got one for running, one for hiking, one for dress, at least one for dance, one for whatever. Do you have more than one pair of shoes? Yes. Are you in the field of electronics technology and electronics engineering seriously as a career move? I hope so. Otherwise, you wouldn't be viewing these videos. So what's another, couple of dollars, a few dollars for a calculator that'll make your work smarter, not harder? But In lieu of this, as long as you have the ENG key on your Sharp calculator, or Sony calculator, or anybody else's calculator, as long as you have the ENG key, you can convert any useless scientific notation with the push of one button into engineering notation. And engineering notation, we said, had to have some power of 10 that is a multiple of 3. There's a 6. And this is useful to us because this is -6. So 10 power -6, if you look up in your journals, because you took the time to write it down carefully, that's a call to action, people. Should have this stuff in your journal. 10 -6 is associated with what engineering prefix? Come on, come on. Micro, okay? It's micro. Next, how do we get the engineering prefix? The engineering prefix is really easy to set up on this calculator, and I'll show you that in just a moment. One more slide first, and that is here. On this calculator, when you first receive it, in order to set this up for prefix notation, all you have to do is to follow this page, and this page comes from not the owner's manual that's attached to the calculator in its box, but this is from the website. It's far more comprehensive. It's like 30, almost 39 pages. Anyway, on this particular page, it shows if we want engineering prefixes to appear, we hit the mode button a number of times until we see DISP. Then we hit number 1, and then we have the ability to click engineering on or engineering off. And I'll show you these steps right now. Let me go ahead and switch to camera mode. All right, so I said previously, for the purpose of our projects, we don't need the mega $100 graphing calculators. This is very popular for engineering students, and if you have this, that's fine. It's wonderful. You'll learn how to use this. The engineering key is specified as "E" on this particular calculator. "E" in order to hit it's a second function, right? And then on the TI Inspire, this particular guy is also designated as a "E". What's nice about this is it happens to have the "E" as its own button. It's not a second function as it would be on the 84. Here's the 84, and here's this. So you don't need mega $100 calculators unless you're going into electrical engineering all the way up to, say, bachelor's and master's level, in which case, yeah, these would be worthwhile investments. But for now, since we're just playing around and seeing if we are enjoying electronics technology and electronics engineering, all you need are calculators similar to this. Now, both of these are Casios, but they do behave differently. They both have an ENG key right here and right here. They both have the time 10 power of X key, which is this one here. Now, on this model, it's designated as time 10 power of X. On this model, EXP. They are identical functions. So on your scientific calculator, which may not be a Casio, let's say it's a Sharp or Sony or some other brand, doesn't matter. As long as your calculator has one of these two, either the EXP or the times 10X, as well as a dedicated ENG key right here and right here, you're in, you're solid, okay? You could do all the work on this type of calculator without the engineering prefixes. But having the engineering prefixes, such as my older model here, or the new one that I just acquired for you guys, and also acquired one for myself, that turns out to be very reasonable price-wise. Turn the puppy on, and let me bring this down. Bring this down here so we can see it a little better. All right, now what I'm going to do is, I think this is, all right, so I'm going to go mode, okay, clear. Here, number 3, I'm going to clear all, reset all. So everything is reset back to factory normal. So in factory normal mode, this is what you're going to see when we go to do the calculation that's specified on the previous page. It was 8 and divide by, so let's say 8 volts divide by, and we said 458, so 458 kilo. How do I enter kilo on this calculator? Shift, and the button here is K for number 6, 6 for K. It appears there as a kilo, then hit equals. When I hit equals, guess what? It shows me something useless. It shows me scientific notation. This is not a power of 10 that is a multiple of 3. It is showing 10 negative 5. So this is useless to me as an answer to jot down. What is useful is if I convert this to engineering notation. So I'm going to convert this to engineering notation simply by hitting the let ENG button. And when I go to do so, aha, guess what? Instead of 1.74, it is now 17.467248. But check out the power of 10. The power of 10 is now negative 6. Negative 6 is a multiple of 3. Negative 6, 10 power is associated with an engineering prefix. Come on now. It's in your notes, and I said it just a couple of slides ago, micro. So this 8 volts divided by 458 kilo works out to be 17.47 microamps. But how do I get this to see the micro that's up here? Easy schmeezy. All you have to do is we follow the directions on this page. You want to hit mode a bunch of times until you see display. So let's go ahead, hit mode a bunch of times. Here, 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 here. Ah, display. When you see display, then you hit 1. So you'd hit 1. And then here's where you see the engineering on, engineering off. Well, guess what? We want engineering on. So we're going to hit number 1. Boom. And guess what, my friends? Look at this. The symbol for micro appears on the screen. Isn't that sweet? So how we do it with a non-metric prefix calculator, like this is a great calculator, it's one of my favorites. Clear, clear, clear. So 8 volts divided by 458. Now I don't have a kilo key. What I have to do is hit a times 10x. So times 10x, and a kilo is what power of 10? Look it up. Come on now, what's a kilo? So if you look it up in your journal, again, you should have those pages dog-eared or flagged with some sort of post-it or something. Kilo works out to be 10 power of 3. So I have 8 divided by 458 times 10 power of 3. So I'm going to hit the 3, and we can see right there 10 power 3. 10 power 3 is the same as kilo on this calculator. And now I'm going to hit equals. Now, when I hit equals, here it shows me that goofy scientific notation that's useless, 1.746, but it's times 10 to negative 5. So how do I convert this into engineering notation? Well, I've got this engineering button right here. Hit this, boom. It shifts the decimal point around and locks in the correct engineering prefix. So 17.46724 microamps. Now, you were shown in a previous topic video how to properly round this off to 2 digits. So this would be rounded off as 17.47 microamps. How do we know it's micro? Well, 10 negative 6, again, you have to go back to your journal, look it up, find 10 negative 6, you see that it's micro. What is the engineering prefix symbol for micro? It's right here, my friends. It looks like a cursive U. And this calculator just saves you a few steps in comparison to the regular calculator. But if you already own a nice calculator like this and you don't feel compelled to change to this, that's perfectly okay. I'm just looking to find the most cost-effective way for you to have metric prefixes available to you on the entry side as well as on the readout side, which is what this provides, without having to do the conversion. Now, truth be told, if you do enough of these calculations back and forth, you'll know millis and micros and kilos and megas and gigas powers of 10 it'll be easily memorized if you do this enough. You'll be using the times 10x key a whole lot. All right, so that's how we set up the calculator into this mode. And let's go ahead and get us back into the share screen. So here, and share, and share. All right, next slide. Okay, we're going to talk about circuit builds. And as we're going to talk about circuit builds, take a look at this. I happen to have two series circuits. They look similar from the top view. They appear very similar. They're built on my half-size boards and have two separate power supplies. That's fine. And there are 3 resistors with an LED. Now, why the LED? The LED, again, is here only to show us initially that we have an on circuit. Once we verify that the circuit connections are good, we can remove the LED for actual measurements. Now, I will show you in a moment 2 different ways of building your circuitry. One way of building your circuitry is, for many students, they start off using the beginner, what we call spaghetti wiring. What is spaghetti wiring? The wiring goes all over the place. And so with these resistors, you would take them out of your kit, as I've shown you in a previous topic video, remove the masking tape schmutz off the ends of them, bend them slightly, and put them into an appropriate pattern that will provide continuity and electricity to flow from the positive rail all the way through to the negative rail. And the LED lights up, power supply is lit up. Now, I'm going to help you graduate from spaghetti wiring into neat wiring. Neat wiring is a more advanced level of wiring. It takes a little bit of effort, not much. Once you get used to doing this, and everything just looks so much nicer. And the neat wiring has the resistors cut, bent, with specific jumper wires in the circuit and down here. So why the neat wiring? Well, when you get into more sophisticated circuit builds, starting off with your circuits being built neat versus the spaghetti method allows you to grow your circuit builds over time, such that in far more complex circuits, like this 555 timer circuit, where this timer chip with various resistor values and various capacitors and 2 LEDs is designed to go click, clock, click, clock, and it does alternate with a timing you can set. The set of the timing, the duration of that clicking back and forth, is set as a combination of this capacitor and one of the resistors. So the combination of the two will set the timing for this to go click, clack, click, clack. And guess what? What would be a practical application for a timer circuit that was clicking and clacking between 2 LEDs? You might find this at a railroad crossing. Yeah, at a railroad crossing, don't the lights go clink, clink, blink, 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 blink? And isn't there a bell that goes dong, 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 dong? Or how about your turn signal? Your turn signal goes clicking on, clicking off, clicking on. Wow. And so guess how those circuits are built? With a little timer chip and probably not spaghetti wiring, I guarantee you. All right. All right. So what we're going to do is show you how these are going to happen in just a moment. Okay, so I'm going to switch the camera to circuit builds on a moment on the breadboards, and I wanted to highlight a couple of things of interest. In order for you to graduate beyond spaghetti wiring into the neat wiring method, you really need to use your your solder, what your kit calls your solderless jumper wires. So in your kits, okay, as I'm going to go to this next video, go to the next camera mode, you want to get your kit out and find this jumper wire kit. It's the solderless jumper wires. We call this pre-cut jumper wires. You're going to need this because these are pre-cut into various lengths, various colors that allow you to have wire connections on the board without those loops of wires that cause that spaghetti complex. And as you can see, compare this to this, this is much neater. And as we graduate from here to more sophisticated circuits, you can see if this were done with the spaghetti method here, this would be very, very bulky to store, bulky to transport, and harder to analyze because the wire loops are in your face. But as the wires are jumpers that are down low, if you were to do troubleshooting or you were to troubleshoot each other's boards, if each of you built something similar to this, now you may have slightly different color wires, slightly different paths, but the end result is the connections will be the same in order to achieve the same result. But let's say one of your friends' boards aren't working properly. Well, if they built this circuit using spaghetti, it'll be really hard and time consuming to troubleshoot. But if they built this board using the neat method, wow, it would be easy to say, hey, this jumper wire is in the wrong position, or that resistor is connected to the wrong hole. It's much easier for you to see where any troubleshooting that needs to take place can take place. All right. All right. So that being said, I'm now going to go to camera mode. All right, so we're back in camera mode, and in camera mode, I had suggested this particular project kit. You may have acquired something differently, or your school may have supplied you something different than this. If you had not anything supplied by your school, or you haven't acquired one yet, you really need to do so. And I have the affiliate link for this in the narration portion of the YouTube video. So this one happens to be very reasonably priced and has tons and tons of stuff. And so what I recommended for our students was to rearrange the packaging of this where you can remove a lot of things that are not immediately useful for you to have in the classroom. What you need to have in the classroom certainly are your LEDs. What you need to have in the classroom is your assortment of resistors. And I said down at the bottom, you should have your jumper wire package down there. You should have your project boards. You should have spring-loaded a small pair of needle nose pliers. And so this is set up in such a way that yes, I can have more than one project board in here. I can have a project board like that, and I can have another project board like this, and then cover it all up. Do this, put a rubber band around this, put this in my backpack, and I'm good to go. What's nice about this is you really ought to learn how to build your project boards at home, because taking the time to build these in lab is an unfortunate waste of time in the lab when you should be using the lab time to interface with your instructor, to use the benchtop equipment for making measurements and following along with the instructions. If you take lab time to build this in the lab, then your focus of attention and time efficiency is diminished quite a bit. So I highly encourage you to read the assignments from your instructor, build these ahead of time so that when they're built, you tuck them in here and life is good. Boom. Oops, forgot. This has to go in here. This has to go in here. And that really is all you need in most cases to take to school. And you're set. Now, what I wanted to show you in particular was this set. And this set down here is the jumper wire set that we will be using. I do highly recommend you get a rubber band around this, because if you don't, and let's say this is open because you are, and I'm holding this very carefully on the tabletop. I'm not holding it up here to open so I can look at it. No, hold it down on the tabletop very carefully. Hold the base, unclip the lid, and very carefully open this up. Do not allow the base to flip up quickly, because if it flips up or flips off the table and all these hundreds of pieces fall on the floor, you will be crying a big, big tear. We don't want that to happen. All right. So in order for us to pull out any kind of jumper that we want, I recommend we hold this with one hand and use our needle nose pliers in an underhand technique like this. And if I wanted a blue jumper, reach down in here and separate a blue jumper. And there I have a blue jumper that I might want to use. And if I wanted to get a green jumper in here, I can go down here and pick out shake this up, I can have a green jumper. If I wanted a red jumper wire, come over here and do this. And use your needle nose pliers rather than use your fingers. Your fingers, especially on big fat fingers, aren't able to get down in here carefully enough to be able to pull them out correctly. Now you see my left hand is holding this down. When I've pulled out jumper wires, immediately, what you want to do is take and cover this and immediately put a rubber band around this, because if this is left open for any reason on your lab bench or your tabletop at home and you knock this over, all these pieces fall on the carpet rather than a nice clean hard floor like you have in lab. If it falls in your carpet, you are definitely crying the big tear, and mama is going to be very upset with you having all these little pieces on her carpeted floor. Okay. All right. So what I'm going to do, carefully open this guy back up, hold the base down, and put these pieces back. So I can put them back by hand. This guy goes here, this guy goes here, this guy goes here, this guy goes here. And that way, oh, a little blue jumper wire, that guy can go there, cover this up, and immediately put this over, and you are a happy camper. And where does it go? It goes in your project kit at the bottom of the box in the back. Okay, like so. Your needle nose pliers goes there. The project that you're working on goes there. Your resistor packs all go here, and your LED goes here, and boom, voila, you are set, ready to go with a nice big rubber band around this in your backpack, and life is good. Okay, now circuit builds. Let's talk about them. Here's one. That's the neat one. Here's one. This is the spaghetti one. And let's bring you close up onto these guys so you can see the difference in the build. All right, let's go ahead and start with this one. This is the most common way that students do build their circuits. It's not wrong, nothing wrong with this at all. I'm just going to show you a way, and I'll show you a better way. So a way right here shows the 3 resistors, and they are correctly pulled out of your kits, out of the correct bags, the 330 ohms, the 100 ohms, an LED just for testing the circuit, and then the 220 ohms over here. And you have to be very careful when you pull them out of their respective bags that you pull them out from one at a time, very carefully, so as not to mix them up. The last thing you want to do is to mix them up. So what I have is, here's the 100 ohm bag, here's the 330 ohm bag, and somewhere on the table, I have my 220 ohm bag. There they are. Okay. So when you need the 330, keep the other ones aside. Only pull out one of the 330s. Remember to remove any adhesive residue that's on either end that was held by the masking tape. Remove the schmutz, give it a bend. When you give it a bend, then you will put it into the board. One end will go into the red power rail. The other end will go somewhere on the board, and I happen to have picked row 24. It's arbitrary, but I happen to pick row number 24 from one end of the resistor to go into. R2 is a 100 ohm resistor, and so we'll get the 100 ohm pack. Here's the 100 ohm pack. Pull out one resistor here, clean off the ends, and give them the bend and make a connection so that R2 is physically connected to R1, which they are through row 24's tie points right there. And this gives nice bend, and it comes over to here. And I happen to have this ending up on what row 18. And row 18, I have an LED. LED jumps over to row 16, and on row 16, then I have one more resistor going to the blue rail. Okay, and I can use this blue rail the same as this blue rail as long as my jumper wires have been set as I've designated for you in a previous video. Okay, All right, so this is set up so that we will be able to light this up once we connect this to power. And we will go ahead and connect this to power. Truly, honestly, it'll happen. All right, so connect this guy to power and turn it on. LED is on. Now, if you've done everything correctly and the LED doesn't light up, remember I said very likely the long lead was in the wrong place. You just simply flip it around so that the long lead is closer to the positive side of the circuit. And the positive rail is here all the way to the end of resistor R2. So the long lead must be connected to, in this case, since R2 is connected to row 18, then the long lead of the LED has to be connected to row 18. And here it lights up. Now, if this guy were in fact backwards, like this, pins are all in the right place, but I have the wrong pin in the wrong place. So I have to have the long pin, flip this guy around to here. Long pin has to go like so, and life is good. Now, I caution you about this for a number of reasons, and that is sometimes when you're playing with resistors that are from our kits, because they are quarter-watt metal film resistors, they happen to be really, really tiny physical resistors, and the wires are very fine. And so when you're putting the resistors onto the board, sometimes with my big fat fingers, I might crinkle something, and that would be horrible. So for example, here's one that has been bent. Now, to try to keep pushing this into a tie point in one of the holes, this just keeps bending more and more. So this is unfortunate. So when this happens, you can use needle nose pliers to try to straighten this out, but you can minimize this dramatically, avoid this dramatically, if you use your needle nose pliers to help put the components down into the board. So yes, I could use my fingers, I could use my hands. Most of the time I do because I'm used to doing this. Here, and guide this along, push this in gently. But sometimes I might give it a little encouragement if the hole is just a little bit challenging. I might grab the needle nose pliers and just pull it and give it a push at the base of a resistor lead just to help it down if it needs some encouragement. Okay, all right, so that's your spaghetti wire approach, and it will work just fine for most of the labs that we're going to be playing with in the next one or two topics. But I tell you, the sooner you can learn to graduate from this into the neat method, which is shown here, then the better. So let me go ahead and light this guy up. Right here. Okay, turn this guy on, and there we are. This guy lights up beautifully, and it's built from a conceptual standpoint very much similar to the other one. What I've done with the resistors is I've pre-cut them to shorter and then bent the leads at 90 degrees and then use my needle nose pliers to push these guys down. So I have my 330 ohm resistor here. I have a jumper wire specifically from here to here. Now, could I connect R2 directly to the end of R1 like I did with this method? Yes, I could. But I'll tell you why we have this in here in a moment. It's for verifying current. And then R2 goes over to here. In this case, goes to row, what do I have here? Row 23. Row 23, I have the long lead of the LED coming down to row 21. And row 21, I've got the 220 ohm resistor going to ground. So these guys are built conceptually, electronically, the same way, but built physically quite different. So this is spaghetti wire approach. This is the need approach, and I highly recommend that you consider using the need approach. And when we go to do measurements, you'll see why this is a benefit to you. So let's go ahead and do this. All right, on this slide, we want to talk about voltages to ground. Voltages to ground. What is GND? GND is the abbreviation for ground. What is ground in electronics? It's defined by this bullet point as a common reference point. Common reference point in a schematic as well as circuits that typically represents the last point connecting back to the voltage source. Can you see the ground symbol here? It is attached to this node. Remember, node is what we call these dots that are connecting points within a circuit. And I've got nodes all over the place. And ground is typically connected to a node, some connecting point that takes us back to the negative side of our voltage source without negatives. Actually, right here, here's a voltage source. The negative side of the voltage source without anything between ground and that negative plate. It is defined here as the point of 0 volts potential, meaning ground has no pressure to move electricity whatsoever. The only pressure that we have to move any kind of electrons in this circuit is from your voltage source. This 5 volt V1 voltage source from the negative plate moves the electrons down and then over. So no voltage here, 0. Ground, voltages to ground. Now that's a very special concept because if you look at the title of the slide, we're talking voltages to ground. Not current flowing to ground, but voltages to ground. What does this mean? Voltage to ground means taking voltage measurements at specific points in the circuit. And here's a phrase you'll hear a lot: with respect to ground. Say that, repeat that. With respect to ground. Okay, very common phrase. Put it in parentheses. Make sure this is in your journal. This allows for very quick troubleshooting by field technicians. You can be out there as a field tech and go through voltage measurements using this method, voltages with respect to ground, and very quickly analyze and troubleshoot where a problem may be in a circuit. So it allows for quick troubleshooting by field technicians by keeping the black probe connected to ground. So it's connected to ground, and probably not with your hand, and probably with a clip of some sort. You just clip the probe onto the ground point, and then with the other hand, using the red probe, just spot check voltages in various parts of the circuit. Most important here, ground in electronics is not the same as earth ground in electrical circuits. Totally different things. So when we say voltages to ground, look at my schematic. Schematic's a little different than before. Before, we had a voltmeter across only R1. We had a voltmeter only across R2 and a voltmeter only across R3. Take a look at voltmeter number 1. Voltmeter number 1 is connected to the top of R1, all the way down to the bottom of the last resistor. In other words, voltmeter number 1 is measuring the voltage across R1, R2, and R3 combined. What should VM1 measure? Well, you can see from the simulator, measures 5 volts. You'll understand why in a moment. Voltmeter number 2 is connected to the top of R2, but where's the back end of the voltmeter connected to ground? Right there, this whole thing is ground. All of these points are ground. This point is ground, this point is ground, this point is ground. Ground is this entire length of wire from the negative terminal of the voltage source all the way to the bottom of each of these, the resistor and each of these voltmeters. This whole line right here is ground, even though we show ground as one symbol here. This whole chunk of wire from this corner all the way to here is ground. So VM2, voltmeter number 2, is connected from the top of R2 to ground. So what do you think it's going to measure? It's going to measure the sum total of the voltage across R1 plus R2. And it calculates to be 2.46 volts. How about the voltmeter R3? The voltmeter R3 is only across the last resistor, so it's the same as what we determined before, 1.69. Voltmeter number 4 is across the top of the source to the bottom of the source on this side, and it verifies that my 5 volts on the left side voltmeter is going to be the same 5 volts as my VM1 on the right side of the voltage divider. Should they both be 5? Yes, here's why. Look at the top of VM1. Voltmeter number 1 is connected to the top of the source, yes? Voltmeter number 1 is connected to, through this node, to the top of the source. So since there's no resistor here between this point and this point, between these two nodes, it is electrically connected to the top of the source. So both VM1 and VM4 are both connected to the top of the voltage source. Now take a look at the bottom of VM4. The bottom of VM4 is connected to ground, which is the negative side of my voltage source in this case. The bottom of VM1, voltmeter number 1, is connected to, through all these wires, to ground. Remember, since there's no component, no resistor in any of these, between any of these nodes, it is electrically the same as being connected to ground, being connected to the negative side of the source. Therefore, voltmeter number 1 and voltmeter number 4 should in fact be the same amount of voltage. So a voltage divider network such as this allows for quick troubleshooting, quick troubleshooting, as long as you know what voltages need to go where and how that's determined. All right, let's go to the next one. And as in review, DMM stands for digital multimeter. Multi meaning it has many functions, multiple functions. And here, to be clear, first bullet point, when we use the DMM to measure voltage, the DMM is referred to as a voltmeter. So when I set this for V, it is being used as a voltmeter. Second bullet point, if I use the multimeter to measure current, then at that moment, the DMM is referred to as an ammeter. Everybody say ammeter. Repeat, ammeter. It's different than voltmeter. So what do you think ammeter? Because it's measuring what? Current. Current is in what units? What's your journal say? Current is in units of amps. Thank goodness you wrote down the electrical units table into your journal and you've memorized it, all right? So when we're using the DMM to measure current, it's called an ammeter. You'll hear these words a lot in the slides forthcoming. And then when we use it to measure resistance, guess what? It is referred to as, read this with me, ohm meter, 2 M's, ohm meter for measuring ohms, all right? All right, now, next. So before we go to the circuit builds on the breadboards and do these measurements, I wanted to show you some other options that you might be thinking about, and that is, notice that I'm using half-size boards. Most of the circuits that we're going to be learning can easily be built on half-size boards, even the more complex ones that I showed you on an earlier slide in this particular video. I had a very complex 555 timer circuit with blinking LEDs flashing back and forth that fits on the half-size board. Why do I want to use half-size boards? Because it allows me to build multiple boards. And so I can have one circuit on one board, another circuit on another board, and they will not interfere with each other. And so there happens to be an Amazon affiliate link if you're looking to have some additional boards. It's not very expensive at all. This particular package happens to give you a second full-size board for those really large projects that might go beyond a single board. So you will have 2 large boards. But here, check this out. It gives you 2 half-size boards, which is what I'm using right here. I've got 2 half-size boards. And the bonus here is that they give you 6 mini boards. And the 6 mini boards are really, really good for small projects where you're not going to attach a power supply directly to this. You might attach a 9-volt battery. You might attach a AA battery pack attached with Velcro to the back side of these. So having the mini boards is really, really handy for projects that are transportable, projects that you would take out in the field, for example, where you don't have a USB connector, you're just powering it by battery. So these are really handy, and I've used these a lot in the past. I do, as you can see, have more than one DC power supply. And there happens to be an Amazon affiliate link where you can acquire additional DC power supplies. Why would it be handy to own one more extra? Because power supplies, like anything else, can fail, and it would be horrible at the moment that some evening you're ready to build a circuit, and also for whatever reason the power supply fails. It's good to have a backup. And this is sold as a 3-pack. And again, click the affiliate link and you'll see it's very reasonably priced. It's a ridiculously low price for a 3-pack. Now, resistors. This is a big one. And I can't emphasize this one enough. And that is this one. These are 1/2 watt resistors. And we'll talk about wattage of resistors in another video. But physically, 1/2 watt resistors are quite a bit bigger than your 1/4 watt resistors, which means there's also heavier wires. So these wires are easier to work with your hands for putting resistors on the board. They're not these really, really fine wires that crumple very easily. The other thing that's really nice about this particular kit is that it happens to have the resistors already in their own compartments. It's like 20 resistors per compartment. And they show you a picture of the color banding of the resistor, as well as the ohmic value, the wattage, as well as the number of pieces. And so very easy to pull one out, put one back, pull one out, put one back. And I'll show you what I do for these in just a moment. Okay, may have done a boo-boo, but let me just double check. If you didn't see this slide while I was talking about multiple breadboards and multiple power supplies and multiple resistor packs, let me just make sure that you are able to see it here. I've got an Amazon affiliate links to multiple breadboards, 2 of the minis, 2 of the smaller 1/2 boards, and 6 minis in one package, 3 power supplies in one package. And most interesting and useful to you will be having physically larger resistors. They're same metal film resistors. They're very precision. They're 1% tolerance, plus or minus 1%, as opposed to the plus or minus 5% carbon resistors. And they are individually segmented into separate compartments in this particular kit arrangement. Now, I'm going to stop the share and into camera mode, show you my resistor pack. So what I use are 1/2 watt resistors, and 1/2 watt resistors I happen to have in this particular case. And again, this is normally rubber banded, but I took off the rubber band already. Happen to have a resistor color code key. Open this guy up. And what I've done with mine, let me show it to you this way. I think you can see I have them compartmentalized from 1 to 8.2 ohms, 10 to 82 ohms, 100 to 820 ohms, 1K to 8.2K, 10K to 82K, 100K, all the way beyond 1 meg. Okay, and so they're marked and compartmentalized, and these are physically larger than the 1/4 watt resistors. These are 1/2 watt resistors, and the 1/2 watt resistors, as you can see, have more stout wires, and they're physically larger and easier to identify. Now, the kit that I've got in the previous slide recommending to you are not the lower quality plus or minus 5% resistors. They happen to be the same quality as the 1% precision resistors you have in your kit, except they're physically larger for better heat dissipation, and the wires are more stout so that they will not crumple as easily as these guys will. If I were to take one of the 1/2 watt resistors and just physically put it on the board, and you can see right here, yeah, oops, come back here, sorry, moved my mouse. Stop that. Go back to screen. Stop here, sorry. Okay, so on the camera, you can see the 1/4 watt resistor half-watt resistor, quite a bit difference. And so the kit that I'm recommending will be the same precision as these, except physically this size and easier to work with on your boards. Okay, so enough of resistors. Now, let's also go to show you these other things. And so I'm just going to go ahead and use the neat one. I'll use both. All right. So we were going to do some measurements, and let's go ahead and see, in fact, where my, let's go to here. All right, so in any circuit, the first thing we're going to determine continuity. And once we determine continuity, we also want to determine to make sure we have the right resistors, right resistor values, and we have the resistors in the correct position on the board. So as you can see, R1 is a 330 ohm resistor, and it's physically connected to the red rail, which is the plus side of the voltage source. Then after R1, 330 ohms, I have a 100 ohm resistor, and after a 100 ohm resistor, I have a 220 ohm resistor, and the 220 ohm resistor is connected to the negative side of the power supply. In fact, with all of these things connected, might be a little difficult to discern. Let me go to a previous one here. Right here. Okay, so if you look at the schematic that's on the far left-hand side is my basic schematic before we hook up meters to this. We have our 5-volt source. The positive side red rail is connected to the top of R1. R1 is connected to R2, connected to R3 in series. And then the bottom of R3, the 220 ohm resistor, is connected back to the blue rail, which takes me back to the negative side of the source. And I'm arbitrarily calling this point here, this dot, ground as my common reference point, okay? We can actually physically attach ground elsewhere, but for the time being, I'm going to attach it here, and we will go to check our circuits. So first thing we need to do, check R1, R2, R3 for their ohms, and let's make sure they are in the right places, okay? Now, in addition to that, we want to make sure that they also total up correctly, because we happen to have this formula right here. R total, see, R total is equal to the sum of R1 plus R2 plus R3. And then through another slide, we had done calculation right here, the voltage divider formula. And voltage divider formula, we used the formula for VR1 as R1 over R total times 5, giving us these various voltages. Now, for that reason, also, we want to make sure that our R total is something close to 650 ohms. R1 something close to 330, R2 close to 100, R3 being close to 220 ohms. And when we measure across all of them, something close to 650. And why do I say close? Because there is a margin of error in the construction of the resistors. It's plus or minus 1%. And there may also be some inconsistencies or something in the board that might be adding to an additional margin of difference. All right, so we just want to verify that the circuits are have continuity. We have current flowing. The LEDs tell us that that is the case. Once the LEDs are lit, when we light up the power supply, like so, and the same thing here, light up our power supply, the LED lights up, then our circuit build is good. What we need to do at this point in time is remove the LED, and turn this off for a moment. We're going to measure resistance. To measure resistance, we said before that you have to have the power supply off, and the power supply needed to be disconnected. So that doesn't mean we have to physically take the power supply off the boards. I would caution you from doing that because we've got 8 pins that have to line up very carefully. And we don't want to pull this on and off the board repeatedly. If you damage any one of those 8, this power supply's performance will be compromised, all right? So we want to keep this on the board. Same thing here, we're going to keep the power supplies on the board. So that being said, how do I disconnect this from the power rail? Because this does connect to the circuitry very easily. All we need to do is to remove one connection. So I'm going to take this and physically move it off the rail. And so now this is physically off the rail. Let it focus. This resistor was pulled from the red rail off the rail. Now it's floating in space. This guy's connected, but it's also floating. This guy's open, connected to the negative rail. But since there is no connection here, one end connected to a rail is not a problem as long as the other end of the resistor is not connected at all. So I'm going to measure the ohms and confirm and see how we do. I'm going to set this guy to the ohm meter position, illuminate. First thing we want to do is, as always, continuity check. It beeps, it lights up. Oops, show you here better. You might not hear the beep, something about the frequency doesn't get picked up by the microphone for some reason, but trust me, I'm going to touch. It's beeping. The display changes from out of limit and the LED lights up. So from OL, no LED, to touch, it's beeping. You might not hear it, but basically 0 ohms and the LED is lit. So I've got continuity. Once that is done, switch to ohms. You can see that this is showing us some quantity of mega ohms. This will adjust appropriately. It may not stay as mega ohms. And I'm going to connect across resistor 1, which is supposed to be a 330 ohm resistor. One here and one here. Hold. And here's where things can get a little inconsistent with the probes. As I'm pushing down, I happen to have this on a plastic canister, so I'm not getting necessarily good connection here. So I'm going to try something else. Hold on just one moment. Do this. Okay, I've switched from the standard probe tips to the mini hooks. And I showed you in a previous training video, a good resource that's again in the Amazon link area where you can expand your set of test leads to include a set of mini hooks. Now, the display might change very slightly, wavering between 334.0 and 333.9. It's a fraction of an ohm difference. If you're tired of watching it flip back and forth, you can press hold and it'll just lock it at some value. Now, this is supposed to be a 330 ohm resistor, and as a 330 ohm resistor, it's off by 4 ohms. So in comparison to 330, we won't sweat the 4 ohm difference. That's okay, it's close enough to 330. So now what I'm going to do is release the hold. And now, as I've said before, it doesn't matter which way we hook up the hooks or probes on a resistor. The resistor is non-polarized. I'll give this a moment. And again, 333.9. We have 334, which is again fraction of an ohm difference. It really makes no difference when you go one lead or the other. Now, that is close to a 330. This should be something close to a 100. Release my hold. 100.5. And then the last one should be something close to 220. 221. How about that? They all measure something close to where they're supposed to be. And if I take, now remember, there was an LED that was here between these two. I'm going to reconnect this over to here. So now I have a continuous path from this wire to this resistor underneath the board to this resistor, underneath the board to this resistor. It's okay, this is on the blue rail. As long as the top end is not connected to the red rail, I do not have any connection of both ends of this to the power supply. And I'm now going to measure the hole, which we said was something close to 650. And let's see where we end up. How about that? 0.652 kilo is 652 ohms. You're saying, what? It doesn't say 652, it says 0.652 kilo. Really? We're going to go there. I'm going to turn on the calculator. Calculator, I'm going to hit 0.652 kilo. So watch this. I'll bring this up just a little bit. Okay, with our calculator, 0.652 second K. Do I have a 0.652 kilo there? Is that 0.65 volt, 652 kilo here? And I said that's 650 ohms, right? Well, the moment I hit equals, this will switch to the appropriate engineering prefix. Ta-da! Okay, there's no kilo, no milli, no micro. It's telling you I've got 652 whole ohms. And we said this should calculate to be 650 ohms total. So we are happy that we have each resistor measured and verified to be in the correct position. And we've also verified that the total ohms is correct for all three in sequence. Okay, everybody happy, camper? 0.652 kilo. It equals is in fact 652 ohms. Ta-da! All right. Now, once we have verified the ohms, then the next thing we need to do is to verify our voltages. So disconnect, go to V for voltage. This says V for voltage. And now I'm going to connect this resistor back to red rail. So now I have a complete connection from the red rail all the way to the blue rail. Here we go. Bring this up close so you can see this. Red rail, first resistor. These two connect on this row. Second, third resistor connect on this row. And this to the blue rail. Now let's check for voltages. So for voltages, connect and tap. All right. So we said earlier, we should have VR1 measuring 2.54 volts. So I'm going to measure the voltage across R1. Now, voltmeter connections are polarity specific. So the red probe has to be on the more positive side of your device. Let me bring this right down here. Let me see this a little better. Bring this over to here. Let it focus. Give it a moment. Ta-da! There it goes. All right, we are on DC volts, and here's my hooks. It doesn't matter whether I hook to the wire of R2. The wire of R2 is the same as the wire of R1. At this point, these two wires are connected, so it's easier for me to reach this. And we said our calculated voltage should have been 2.54. Oops, silly me, wrong polarity. I'll leave it here for a sec. I got so excited I forgot my polarity. You see a negative here? If you see a negative, it just simply means the wire, the probes are reversed. Keep in mind, I said that the voltage is polarized, so we needed to have the red probe there on the positive side of the resistor and the black probe here, negative side of the resistor. And hold. All right. Supposed to be 2.54, and I'm measuring 2.55, 2.553. I'm going to share it for just a moment. Let's confirm to the slide. The slide says right here, 2.54 volts for voltage number one. The next one we calculated for VR2 is supposed to be 769.23 millivolts. Let's see if that works out to be the case. All right, so I'm going to disconnect from here. Disconnect from here. You got to be careful with these hooks or any kind of a grabbing device like an alligator with these leads. They're so fine. I've yanked that resistor right out of the red rail. So I just got to make sure that goes back down. And now carefully do this guy here and release my hold. Do this guy here. Well, look at this. And let me press hold for a moment. It shows 0.764 V. what is 0.764V? Is that anything close to 769.23 millivolts? Well, again, we bring in our handy dandy calculator and clear, and I'm going to key in 0.764. Okay, 0.764. There's no prefix here, so I'm just going to hit enter. Now, when I hit enter, this calculator should automatically convert to proper engineering notation. Click. Look at that. Look at that. 764 millivolts. 764 millivolts. And if we compare that 764 to our calculated on the slide, just as a refresh, calculated on the side was 769 and change. We measured 764 milli. That's pretty darn good. All right. Remember, this is not an exact science. We just want to be within the ballpark, and we certainly are. So my 764 millivolts, I'm pretty happy with that. And the very last one should be 1.69 volts. So release my hold, release the hold, and take these, and I'll clip this here and here. And again, once I clip, I can let go of my hands, wait for this to stabilize. Make sure I'm not jiggling the wires anywhere. They may be. All right. So I have 1.63 volts, and that's measured across the third resistor. And I'm going to double check my 1.633. Over here I have 1.69. All right. That, again, that's close. It is proportional. It's something in the 1.6 range, and we're happy with the measurement. Cool. Next, we said also that the current is the same in all parts of a series circuit. And let's see if we can confirm that. If I go to this particular slide for just a moment. Okay, looking at this slide, you can see over here that in a series circuit, current is the same, and it's throughout a series circuit. And the simulator measured it in sim as 7.69 milliamps. And I have an ammeter in different parts of the circuit to verify that it doesn't matter where the ammeter is placed in the circuit, because there is only one current path in a series circuit. That current is the same in the series circuit. Now, these are the results that came to us from the simulator. We also calculated this in a subsequent slide. We calculated it here. The I total is V total divided by R total. We calculated this as 5 divided by 650 ohms, gave us 7.69 milliamps as being the current. All right, so what we're going to do is we're going to go to stop the share and now set this up for measuring current. So what I'm going to do is get this set up in just a moment. All right, my friends, before we go to start to measure current, in a previous video, I was demonstrating that and had accidentally used the pointer tip of my probe as a pointer on the circuit where to make connections, where not to make connections. And instead of using the probe tip as a pointer, I should have used a pen. Because I used the probe tip as a pointer, I happened to touch part of the circuit which caused the fuse, the internal fuse of the ammeter to blow. And once that blows, you can measure current anymore until you replace that fuse. So what I'm going to do is I'm going to show you step by step, real time, with this particular multimeter, which is not dissimilar to many other multimeters, functionally and structurally, how to change the fuse. And so we're going to do this with the timer. And so right now it was last set up. We measured resistance, we measured voltages, and now we're going to measure current. So, and we decided, oh, wow, it's not measuring current. perhaps the fuse is blown. So I'm going to start. Okay, first thing we're going to do, remove our leads, set them aside, turn this guy into the off position. Now on this particular multimeter, pull out this way to release the jacket, pull out this way to release the jacket on this side. So now it's released on both sides. Then what we're going to do is pull out the jacket here, pull out the jacket here, and push from the bottom upwards, and the bottom of the multimeter will pop out of the jacket like so. And we're just going to lift it out this way. So now we set this guy aside, and now all we have to do on this is to pull out these screws and go ahead and do this. And I highly recommend a little magnetic tray of some sort. This is from, you can get something like this from Harbor Freight. You can sticks to it. That's got a magnet base, or you can get this from Daiso. That's got a nice magnetic base to it. Nice thing is when you pull this out and you set your screws someplace, they will stay captured and not fall away. So I'm going to do this and captured on the side. Now it's going to be in there, and do this guy here. And there, captured by the tray. And captured by the tray. Now all critical screws are removed. We don't have to, in this particular case, remove the hinge base and this set screw for the battery. This is designed in such a way that this comes apart without having to do that. So you just very gently pry this apart like so, and a little bit more on this side and a little bit more on this side. Lo and behold, there you go. The clamshell is now opened, and what you've got going on here is there is the fuse. How do we know which one? Well, I showed you this before, but you want to pop open each one, and you're going to read whatever is on the board down below. Just flip them up. If you hold this up, you can see, let this focus for a moment. This side is 10 amps, and this side is about 400 milliamps, or typically what most engineers use is 0.5 amps. So this is the ammeter fuse. This is the circuit fuse. Just leave that one in there. Take this guy, pull it out, because it's probably the what's offending us. And you have your kit of replacement fuses. I have the link for this in the Amazon affiliate link. Should always have these handy. And this guy pops in here. Big hammy fingers. Okay, take it, pop it in there, make sure it's secure. Down. There it is. All right, now put the thing together. And before we go to fasten everything, let's go ahead and do a quick ammeter test. And quick ammeter test. Let's go ahead and do this. Pop this guy in here. Pop this guy in here. And let's go ahead, bring this guy in place. Remember, break the circuit open. And at the open, connect your ammeter leads. So this goes on the positive side of the open. This guy goes on the negative side of the open. Take off the hold, and we have did I put back in the wrong fuse? I don't think so. Let's go ahead. This guy goes down, this guy goes down, and then here, good time for troubleshooting. This is good. Ah, there we go. This one lead was popped out for just a bit. Lo and behold, 7.83 milliamps. Press hold. And that's it. Your fuse has been replaced, and you verified that the ammeter is working properly. Took just a few seconds longer because one wire had popped out. And once you make sure everything is firmly where it's supposed to be, it measures just fine. And then we calculated 7.69. This is measuring 7.83. Again, within the ballpark, we're happy campers. All right, so now pull this guy apart. Set this aside, and let's go ahead and resume. All right, turn this guy into the off position. Yeah, don't bother putting it all back together unless you confirm that it is working properly. Otherwise, they'll just have to take time to take it apart again. And we don't want to do that. All right, pop this guy back in like so. Okay, and take this guy. Magnetic tip. Go here and hold it with the hand and lock this guy down there. And one more here. And that guy goes down there. And one of the screws went to the base. Set this guy there. Hold gently and set this in. Ta-da. Take this head first into the jacket like so. Push it all the way up and then wrap the bottom and squeeze it in like so. And gently squeeze the pieces back together. And we are done. Well, reason why it took more than 6 minutes is because I did the circuit check, but realistically, if something unfortunate were to happen and your fuse gets blown, all you have to do is to have a set of spare fuses and you're set to go. So now we're going to move forward and measure current. And if we have some unfortunate accident, yes, you'll have spare fuses, and that's how easy it is to change your fuse on a digital multimeter. Cool. All right. Let's go ahead and do this. All right, so resuming our current measurement, have 7.76 milliamps for the measurement, and we will go ahead and check the current in another part of the circuit. So that means I want to break the circuit open elsewhere. So I presently have this open where the LED used to be. So I'm going to disconnect here, release my hold. Right now it's measuring nothing. I have to rebuild this connection. I'm taking this resistor and moving it over to be the same row. Come on, focus. Oh, there we go. Yes, it's on the same row as R2. And now I'm going to break the circuit open here between R1 and R2. What I'm going to do is pull up one lead of R2 and pull it over. Now I have a physical separation between where R1 hooks up and where R2 is. They are not on the same row. You can see I have a gap here, but I had to rebuild this one, so there's no gap here. You can only have one gap, one open in a circuit at a time. So which lead of these two resistors do I hook the red probe up to? Which side of this gap is more positive? The more positive side is the one closer to R1, and the more negative side of the gap is the one here. And I get my 7.82, close to what I measured before. Don't leave it on for any extended period of time. Rebuild this. Here we go. And let's say I wanted to measure it from the top of the circuit. I can do that by breaking this open here so that this is disconnected from the rail. And then what I can do is I can put in a jumper wire just physically into the red pin. And so where is my gap now? My gap now is physically here. This is where the red rail, where the resistor was physically previously on the red rail. I removed the resistor from the red rail and placed it here. This resistor is no longer connected to the red rail. I have the red wire just hanging there. The other end is not connected to anything. I'm just going to use that piece of metal as a connecting point. And so what I'm going to do is hook up my red hook there and hook up my black hook to the resistor right there. And again, something close to my 7.80 something that I had earlier. That shows that the current is the same from the top to the first resistor. I'm going to unclip, remove this, rebuild this so that this is again on the red rail. So I have R1 on the red rail, over here connected to R2, over here connected to R3. What I'm going to do is I'm going to disconnect this from the blue rail. So here I'm just going to put it somewhere on the board. So now I have a gap. I have a gap from where this third lead of this last lead of the third resistor was previously connected to the blue rail. All I have to do is have a pin in here. I'm going to put a pin in here. And so now I have a gap. The gap is physically right here between this wire of R3 and this wire of the blue rail. There is my gap. This is the only place where I can hook up my probes. Which side of this gap is more positive? This lead of the resistor is more positive because it's still physically connected to the rest of the circuit at the top. Oops, sorry, losing it. And then this lead down here is connected to the blue rail. This is my gap. Okay, remember, this probe does not go anywhere near the red rail if this probe is at the blue rail. That'll blow out the meter for sure. So my gap is here. This guy goes connecting to here, and if everything connects properly, hello. Is this in far enough? Is it in far enough? It's a question. Not being facetious. Let's go to here. Okay. I didn't have enough metal here exposed to grab the mini hook properly. So I'm just hooking up the mini hook to the other end of this jumper wire. And so this mini hook at this end of the jumper wire is the same as touching down here. In fact, this end looks a little longer. So let me change this. Come down here. Okay. And now let me grab this here. Right down onto, yes. And there is my connection of the ammeter to the open. The red hook is on the positive side of the open. The black hook is on the negative side of the open, which is my blue rail. And my current is showing beautifully. So yes, we've proven that current is the same in all parts of a series circuit. And because the ammeter is so delicate for measuring current, if a fuse should blow, like I say, you fortunately have a set of backup fuses, and I think they gave me 20 in this particular pack. And of course, yes, the Amazon affiliate link to the spare fuses is in the narrative portion of our YouTube. Okay, that being said, now let's move on. I think that we have, oh, we got a challenge for you. Haha, yes, let me show you your challenge. You think you learned something? All right, I hope you learned something. Well, if you've taken good notes in your journal and paid very close attention, here, let's see, is this my share? Hold on. Stop share, do a share. And I want this screen. Okay, hit share. Yep, here we are. So this is your challenge voltage divider analysis number 1. looks similar, but is different from yours. It is showing you you're going to use two of your 220 ohm resistors. So you're going to replace R1 as a 220 ohm resistor. You're going to move the 330 ohm resistor from the R1 position now to become R2. You have an R3 that is also a 220 ohm resistor. So because we have different ohms in different places, you're going to do a whole set of new calculations to see if you were getting the gist of what I'm hoping that you would be learning. So you calculate in this sequence. The very first thing you need to do, voltage total is voltage source, which is how many volts? Fill that in. R total is the sum of R1, R2, R3. Well, R1 is 220, R2 is 330, R3 is 220. You sum them out and you write down the total ohms. You need RT because in order to do voltage divider, you're going to divide R1 into RT and then multiply by voltage total to calculate a value. For voltage across R2, you're going to take the ohmic value of R2, which is 330 in this case, divide by the total. Now, the total is no longer 650 ohms. You'll have to figure out what the total is. It's a new total from before. Pop that in here, times your 5, calculate a number. So you're going to do the same here. So you have the voltage total, R total, the voltage across R1, R2, and R3. Now, what you're also going to do is use the point voltage analysis, meaning how much voltage do you anticipate for VM1 to have from here to ground, VM2 from this point to ground, and VM3 from this point to ground. So voltmeter number 1 is across how many resistors? 3 resistors from the top of R1 all the way down to the end of the last resistor. So VM1, voltmeter number 1 is across 3 resistors to ground. Give us a number. Voltmeter number 2 is across 2 resistors. Calculate a number. Voltmeter number 3 is across 1 resistor. Calculate a number. Then, as you measure your R1, R2, and RT, are they close to the measurements of what you hope? Does R1 actually measure something close to 220 as R3? And does R2 measure something close to 330? And is the total measured close to your calculated total? Then measure voltage across R1, R2, R3, and total, like I had shown you. Are the measurements close? Then measure VM1, VM2, VM3, as it's drawn in this schematic, and are your measurements close? If not, then you're going to need to review the analysis that was explained earlier in the video and redo this. Okay, and let's go on to the next. I think I've got another challenge for you. Yes, this is a design challenge. Okay, here's a thought question for you, just to see how well you're processing this information. You're asked to design a circuit now. Yes, you're a designer and analytical technician. It says you're going to design and then you're going to build this circuit that's shown in the schematic that specifies your voltage source is 5, because our power supply on the board is 5. The mystery resistance, we don't know what that number should be, but the desired current must be something close to 30 milliamps. So here, voltage is 5 volts, and I, here's your Ohm's law circle, I is current. Current must be something close to 30 milliamps. So how do you determine R? Well, if you go back to Ohm's law, like we'd shown you before, here's your triangle. If you're looking for R, what do? You put your thumb over the letter R, you look at what's left, and you see that R is equal to a V over an I. The formula shows you R equals V over I. Do you have a V? Do you have an I? Good deal. That allows you to calculate some number of ohms. I'm not going to give that to you. You need to calculate this. That's why this is called a design and a challenge design and analysis. And then if you have questions that pop up on either one of these, you can ask them in the chat. But here we go. You need to figure out, once you calculate that value, how are you going to build this on the board physically? How are you going to get that number of ohms on the board in series? Now, you can use more than one resistor in series, like we had earlier. We had 3 resistors in series all along, and in the previous challenge, we had 3 resistors. How many resistors in series do you think you're going to need to hook up to try to get this as the correct number of resistance so that the current will be close to 30 milliamps? Think about that. The question then also becomes, do you have the right count of the right value resistors to put in series in order for you to do this? Can you build this? And verify that your series resistors that you built are something close to the ohms that we need. All right, so just to show you this can be done. Pardon me. Here we go. I have a cover. The cover hides my solution. I happen to have the hooks in place to measure current, similarly to what we've done previously. But here, the question has to do with what resistors are underneath the cover to achieve a current as close to 30 milliamps as possible. How are you doing this? All right. If you haven't figured this out by now, it's not that hard. If you look at the title of this topic number 5, what's it say? The title of topic number 5 says voltage divider, comma, potentiometer, comma, shorts, and ground analysis. Well, we covered voltage dividers and we covered ground. We'll talk about shorts in a moment, but what is this thing called the potentiometer? Okay. We'll figure that out in just a moment. Let's go ahead and stop the share and show you in your kit, you happen to have a very nice potentiometer. This is your potentiometer. This little blue thing with 3 pins coming out of the bottom. There's your 3 pins coming out of the bottom, and they're staggered, is a potentiometer. What is a potentiometer? It's affectionately abbreviated as POT, P-O-T, and it is a variable resistor. Okay. And let's go ahead and do this. Oh, slideshow from current slide. Okay, so that's your task. Your task is to figure out what is a potentiometer? You'll have to do some research. You'll have to do some research as to how it works. And then your task is to figure out how to build it into your circuit in such a way that you will be able to prove that the amount of ohms is appropriate to show a current flowing through it that is something close to 30 milliamps, such as what's shown here. So, my friends, this is what you got going. Pay attention, pay close attention now. Your task is to do challenge voltage divider analysis number 1. Do all the calculations, do the measurements, check and see how close you are. And then your other task is to design and build an appropriate circuit that will give you 30 milliamps. And you will see the solutions to these in the next video coming up. Now, before we close, I do want to introduce you to the concept of a short circuit. You may have heard the term short circuit before. Here is the definition. Short circuits, it is a very common fault condition, is not what we want, okay? So a short circuit, as defined, is where a low or zero resistance wire, nicknamed a short, is either accidentally or intentionally introduced to the circuit. A paper clip falling on your circuit board would be unintentional. Okay, so that would be an example of an unintentional short introduced to your circuit. And the short, when that happens, if that wire were to fall or paper clip were to fall or staple were to fall on your circuit board, at the time that you're doing your analysis, it could provide an unintended near zero resistance current path that can result in excessive current flow through it that can damage or destroy your electronic circuit or the device. Bad news, okay? So what we've got here is another software I'm using, and it goes to show I've got two resistors, and given the two resistors, normally with the 12-volt supply, I've got 2 voltmeters and I've got an ammeter. And the voltmeter number 1 across this one shows 4 volts. Voltmeter number 2 shows 8 volts. You should verify whether or not these make sense. You should use voltage divider, calculate 1 ohm, divide by 3 kilo ohms. 1 kilo divide by 3 kilo times 12. Does that give you 4? Here, would voltage divider take 2 kilo, divide by the sum, which is 3 kilo, times 12, does that give you 8? So verify that. Verify through calculation that this should be 4 milliamps. So 12 volts divided by 3 kilo, IT should be 12 divided by 3 kilo. Verify you've got 4 milliamps on your calculator, and we have 4 milliamps here. So under normal happy conditions, this is what we should have. Now let me introduce a short and show you where the problem begins. Here we go. We're going to put a short in here. There's going to be a wire between points A and B. This is totally unintended. It previously was not there. Okay, so look at here. There was no wire between here to here. R2 is happy by itself through the ammeter to ground. I'm going to introduce a wire between here and here. It is called a short because it will cause problems. So by having this wire in here, I've got a short. A short has been placed between points A and B. Here's point A, here's point B. And what will happen is the short will cause the electron current flow to bypass R2. R2 being bypassed has been what we call shorted out. So follow the current path. The current path, again, comes from the negative plate down here, doesn't go to ground. It comes down through this wire, through the ammeter, and once it hits node B, it's going to come straight up here to point A. Why will no current flow through this resistor? Because the resistor's got 2,000 ohms of resistance, whereas this wire path, this short, has got 0 ohms. So the current will take the path of 0 resistance. The current will follow this 0 ohm wire straight through here and bypass R2. So R2 has been bypassed. R2 has been shorted out, is the expression we use. So now the only current that's flowing in this case is flowing through one resistor, only through R1. It's no longer flowing through R2. So how does that change the game? Well, hey, it changes the game because there's only one resistor in here now. R1 gets all of the 12 volts. R2 gets none of the 12 volts. And how does the current calculate? The current calculates as 12 volts divided by 1K ohms for the ohms is 12 milliamps. So the current changed from 4 milliamps all the way up to 12 milliamps. Current has risen. And so you got to be careful when shorts are introduced to a circuit that the current doesn't rise so high that it drains your power supply and burns it out, or current rises so high that it can burn out a resistor. Now, let me show you the next one. The next one's pretty extreme. The most extreme is something known as a dead short. This is where you take the battery terminals of your car and put a screwdriver across the terminals. Bad news. That's called the dead short, because what's going to happen to your car battery? Well, it'll probably explode. But after it explodes, it's dead. Okay, you don't want to be anywhere near that. Well, the same thing can happen in electronics. That staple or that paper clip can fall right across the terminals of your voltage source, which is what I have here. This wire is between. Why would any electricity flow to point D and continue through all of these other components going back to point C when it has a 0 ohm path in a circle here on the left? So by having 0 ohms between in a connected path between the negative plate all the way to the positive plate, the ohms have gone to 0, and the current has briefly gone to infinity amps, causing the voltage source to be damaged or destroyed if there's no protection elements in the voltage source, like a built-in fuse or something. So this is a dead short. Do not replicate this on your breadboards because you will damage your power supply irreparably. All right, so this is the last slide of the sequence. So let me make sure you understand your homework for the next go around. Your homework in review are these challenges. This one here, voltage divider challenge number 1. Do these calculations, build the circuit, make these measurements, see if everything comes close for voltages, ohms, and then also current. All right. And if you happen to blow a fuse, well, now you know how to very quickly, in less than 6 minutes, replace your fuse. And then the other assignment is design analysis number 2. Design analysis number 2 is, are you going to have the right count of many ohms in sequence in order to achieve the RT that's necessary to bring this to 30 milliamps? Or are you going to do something more elegant, such as using something called the potentiometer? And I physically showed you one. Yeah, it's in your kit, you have one, but you're going to need to do the research on your own and find out how it works and how to connect it so that you can achieve this measurement that I have underneath this cover, and we'll show you the solutions to both of these challenges in the next training video. So with that, thank you very much. Hopefully this has been useful to you, and if it has, please give me a thumbs up, and even better, hit subscribe, because when you do that, the thumbs up and the subscribe, they both help channel information to YouTube that helps you and future classmates more easily track and find these videos if you find them helpful. And if you want to buy this instructor a cup of coffee, then think about the affiliate links and or join the Patreon page. All right. So with that, thank you so much again. I look forward to seeing you in the next go around. So with that, adios, adieu, and have a wonderful day.